Alright, hello. So we're going to move on with part 2 of section 2, looking at the wave nature of light. We're going to talk about polarization and shifting of light, so a little bit about the Doppler effect of light. So we've already talked about it in terms of sound, and now we're going to talk about it in terms of light. So first let's talk about polarization of light. So you may have like polarized sunglasses, and if you use those to like look at your phone or some sort of screen, sometimes it makes the screen look really weird, and this is due to what's called polarization. And this is production of light in a single plane of oscillation. And so a polarizing medium allows only components of waves of light traveling in the same direction as the polarizing axis to pass through. So basically, in general, what that means is that if you put this medium on here that has is blocking certain waves, if the wave can travel through like this, then it's going to pass through. But if the wave is trying to travel this way, it's going to hit this and not be able to travel through. And this can be used to block certain like colors of light or wavelengths of light, things like that. So polarizing medium produces light that is polarized through this because of this polarizing filter. And then the reflected light, so something like this that would be hitting it, would also be partially polarized. So photographers can use polarizing filters over camera lenses to block reflected light. They can also block certain other colors or types of light and make a photograph look different. Okay, well, we can use more than one polarizing filter, and this is Malice's law. So if we place a second polarized filter over a polarized light, so one that has already been through one polarized filter, if the two filters are parallel, then the light is going to pass through. So, maybe you've got one and it's allowing certain wavelengths, and then maybe you've got, a second polarizing filter, still parallel but different in some ways, so it's still going to allow some of that light to pass through. Well, let's say we have one polarizing filter this way, and then we do another one this direction. So now they're perpendicular. Well, basically, if you put those two together, you're forming this grid where basically no wavelength of light can pass through. So you're blocking things completely. And so Malice's law explains the reduction of light intensity as it passes through a second polarizing filter. So we're kind of reducing what waves can pass through every time we apply one of these filters. And so there's an equation we can use to look at the relationship between the two intensities. So I2 is the intensity of the light after the second polarizing filter, and this is equal to the intensity after the first polarizing filter times cosine of the angle between the two filters. Okay, so from the first filter, and then what's the angle of the second filter in relationship to that first one? And that's cosine 2 times theta. Okay, so let's look at the speed of light. We've already talked about this a little bit. We know that wavelength is a function of the speed of light. We know that speed is equal to wavelength times frequency, and then for speed we can substitute c because that's the speed of light. And so then c is equal to wavelength times frequency, and you can rearrange your equation from there. So wavelength would then equal speed over frequency. So in a vacuum, we know that all light travels at the same speed, which is this c, which is 3 times 10 to the 8th meters per second. So that's the speed of light. Okay, so let's talk a little bit about the Doppler effects. We've already talked about this for sound. For sound, we have to think about the velocities of the source and the detector, and then also the medium that the sound is traveling through, and usually we said this was air at 20 Celsius. So for light, we take some of those variables out, and that's because light and sound are different. So the Doppler effect of light can involve only the velocities of the source and the observer relative to each other. We don't look at the medium because light waves don't vibrate particles or cause these differences in pressure. That's how sound waves work, but light waves don't need a medium to travel through because they can travel in a vacuum, whereas sound can't. And so relative speed then, since we're just looking at the difference between the source and the observer, the relative speed is the magnitude or the amount of the difference between velocities for the source and the observer. So we're just going to basically discount the medium that they're traveling through. So let's look at this. So if we wanted to find frequency, or the observed frequency, so like of you observing light, this is f, so actual frequency, times 1 plus or minus v over c. Okay, so let's talk about when you would make it positive and when you would make it negative. Okay, so it would be positive if the relative speed between the source and the observer, if they're moving toward each other, then we would say that it's 1 plus v over c. So it becomes 1 minus v over c if they're moving away from each other. So, if you're standing here and there's a light moving towards you, we would say that's positive. If you're standing here and the light's moving away from you, then we would say that it's negative. We can also look at wavelength and talk about Doppler shift. And so the change in wavelength is plus or minus v over c times wavelength. And so our change in wavelength is observed minus actual. So your change, which is observed minus actual, is plus or minus v over c times wavelength actual. So we would use plus there if the light is what we call redshifted, which means it's moving away from the observer, and that means that you're going to observe a lower frequency. We would say that it's negative if it is blue shifted, which means it's moving toward the observer. So you can see that between frequency and wavelength, we're going to do opposites. With frequency, positive was moving toward, and here positive is moving away. So for the Doppler shift, a spectrometer, which we did this in chemistry, you looked at those gas discharge tubes and use a spectrometer to break that light up into all the visible spectrum wavelengths for that particular element. Same idea, only they use a much more powerful one, and they can look at stars and determine not only what elements compose the star, but also what direction the star is moving, based on if the light redshifts or blue shifts. And so if it redshifts, that means that the stars are moving away, and if it blue shifts, it means that they're moving closer. And so Hubble used this information to, in 1929, say that the universe was constantly expanding, which was a pretty big idea, and still can be now, depending on other things that you believe. And so he said this because he analyzed emission spectra from galaxies, that's using the spectroscope to look at the stars, and he noticed that all the galaxies and stars that he was looking at were sending redshifted light to Earth, which means that, relative to Earth, those stars are moving away. And so he made that assumption that this means that the universe is constantly expanding because everything is moving away from our reference point. Okay, so we are going to do these practice problems in class, and then this is what you guys are going to work on individually. All right, have a good day.